going to stop the first series of lectures on this subject of the postulates, which was what we talked about last lecture. And we raised a few flags in the last lecture, particularly about eigenkets associated with operators that have a continuous spectrum. We brought up this subject in a bit of detail, and you'll remember it was discussed sort of explicitly in the postulates about discrete and continuous spectrums. And in both cases, we know, because of the postulates, that they are observables. I mean, we have observables, Hermitian operators, with continuous spectrums, and those eigenvectors form a basis for our state space. So we've got that issue, but we've also have the issue that the eigenkets themselves do not represent physically plausible states. So I thought we'd play around a little bit more with this idea of the continuous spectrum, just a few more topics to get comfortable with it, because it is an important point, because ultimately we need to study scattering theory, where these kinds of states show up again. So let's begin. So let's begin by looking at the operator that is sort of the quintessential operator with a continuous spectra, and that is the position operator. So just to get the language straight, there's some observable out there that we might call script x. What would a script x look like? Right, so we might call this the observable position. The observable has associated with it an operator, which is this guy, and then the operator operates on its eigenstates to give you measurements that are the eigenvalues and returns the eigenstates, right? So this is by assumption, right? If this is an observable, ergo it must have a Hermitian operator that acts on the vector space of physical states. And the question is, are these physical states? And we've decided they are not, because they're not square integrable, right? We can't use the probabilistic interpretation on those states, ergo we don't treat them as physical states. However, they are a basis by assumption of the Hilbert space. And when I say by assumption, there is the ability to prove that, right? There is more rigorous forms of the foundations of quantum mechanics that that show that you can extend the vector space that we deal with in quantum mechanics to capture these guys. And but we're not going to do it. I made some references at the end of the last lecture. But now let's talk about, so this is our classic continuous spectrum operator, right? There's others, right? But this is the one we're going to study right now. So now we're going to say, well, let's look at some other operators that would operate on the position eigenkets. And the most obvious one to think of is the translation operator. And we'll write down the translation operator with this script T, which I know I'm going to be sorry I chose, but that is kind of what Sakurai does, and I feel very little compunction, very little reason. There's no compelling reason to not do it the way Sakurai does it. So this translation operator, what do we want this thing to do? Well, we want it to operate on eigenkets of position and return other eigenkets of position. And the new eigenket of position has got to be the old eigen, the new eigen, the eigenket translated to a different position, right? So if this was at position x, this will be the eigenket for position x plus delta x. So if we applied if we applied the position operator on this, then the answer we would get is the number the number x plus delta x times the ket x plus delta x. In other words, this guy here is still an eigenket of position. It's just a different position shifted by delta x. That's the intent of the translation operator. And notice this operates the way we expect. Operators operate on kets and return other kets. And it just so happens it returns another basis ket of the translation operator, another basis ket of the vector space that's just part of the spectral system of the position operator. So this is the way we want the translation operator to work. What properties do we want the translation operator to have? Well, there's really about 4, of which we're going to focus on 2. Now, the first property that we're interested in is that if we have a physical state alpha and we execute the translation operator on alpha, right? In other words, we calculate this new ket, right? Translation operator operating on alpha. And we find the inner product of that new ket with itself, right? And that the bra associated with that new ket, of course, is the adjoint of the translation operator acting on the bra. We're going to get a complex number, right? And that complex number really should equal the complex number of the inner product of the ket with itself, the magnitude, the size of the ket, right? And these two complex numbers should be equal. In other words, we are not expecting that just because you translated some state, that you're going to change the normalization of the state. The normalization should be preserved, right? And of course, the way I've written it here, in this circumstance, this normalization we're expecting to be 1, right? But if this was a state, say, instead of alpha, say this state over here was Bravo, right? And then this was Bravo here. There would be some other number, right, that wouldn't be 1 because the overlap of the state alpha with Bravo won't necessarily be 1. And we would expect whatever that number to be still be conserved. So we're expecting the conservation of this normalization when we use this combined operator of the adjoint of the translation operator and the translation operator itself. Now notice we said nothing about the nature of the translation operator. This is an example of an operator that's not Hermitian, right? Now it may have a basis we don't know about, but we're just talking about how it operates on position eigenkets. And notice that we threw down arbitrary physical states here. So when you see that and you understand the definition is based on position eigenkets, you know that somewhere along the line we're going to go with inserting a complete set of states, so to speak, right? Like this, right there on alpha. And now we have a complex number here, and we have an exposed eigenket, and we know how the operation works on that exposed eigenket. So we know, so whenever you see these states, you immediately think of what does it break down into a basis. And in this particular case, the basis we're using is the complete set of states associated with the position operator, right? And so you should never be intimidated when you see just some arbitrary state out there, because you know by the postulates of quantum mechanics, you can immediately write this down, because this guy here, this guy right here, that's just the identity matrix, right? That's why this is so powerful, and that's why Sakurai likes to say you can't understate the significance of this integral being the complete set of states, although you can state the significance of forgetting to write down the differential there. Otherwise, it makes no sense. Okay, so this is one property we definitely want our translation operator to have. And then the other property we're interested in is that if you operate on a state ket with a translation of delta x double prime, and then you operate again on the new state ket with delta x prime translation, there's a single translation operator that will have worked on the first state ket but has a larger displacement, right? That's a very additive thing. And this immediately, when you kind of see stuff like this, you think exponential right away, right? And so there are hints here about what you should do next. But these are the two properties we're going to study the most. There are a couple other properties that actually follow from this, but let's look at these two first. And if I were to simplify the first one, right, then what would I see? I would see that this translation operator times its adjoint equals the identity, right? The identity has to land here in the middle of this mess, or in the middle of the bra ket, in order to preserve this probability. And whenever an operator times its adjoint is the identity, we say it's a unitary operator. And this constraint to being a unitary operator, get used to that. This is QED prerequisite stuff. Operators of many operators have to have this kind of property. The preservation of probability is sometimes the way it's called. In order for quantum mechanics to work, most of the operators we deal with must be unitary. And they don't all have to be Hermitian, just the observables, right? But here's an example so far of an operator that is not Hermitian, but it's definitely unitary. Another way of expressing unitarity is that the adjoint of the operator equals the inverse of the operator, right? You multiply both sides by the operator inverse and you get this expression. So that's the first important point. And then you have this one too. So how do we figure out what T is, right? We want to figure out, we don't want T to be completely abstract. The observables can be completely abstract, right? You don't need to express the observables with some tricky operator. You just establish them in their own Ket system. And this is basically all you need to say about the observable, right? You know these Kets exist because of the postulates, and you know this operation exists because we postulate that the observable is Hermitian. Not so with the translation operator. We just find it the way we want it to act. We assume that it's linear, right? But we need to figure out a little more specifically about how it acts. And that's hard. But when you study the unitarity and when you look at this, some smart guys came up with a candidate operator, an operator that probably should meet these properties and we could accept as the translation operator. So this is our proposed candidate for the translation operator. It's a little bit of a push, right? What we're doing is we're saying it's the identity operator minus the imaginary number times some other operator that's unspecified times the amount of the shift. And what we're trying to see is if this operator here satisfies these properties. Obviously, we're kind of pushing all the mystery into this operator k, which I should indicate with a little hat. So this is pretty typical sometimes of mathematical physics, is that they try to tighten the mystery into as small a spot as possible. And right now, we know that this operator has these properties, and we think that this is a way of decomposing this operator such that we're narrowing the properties to something that's a little more, something we can handle a little more. That's the idea, at least. But we need to sort of experiment with this to see if it's true. So what we're going to do is we're going to check, does this operator satisfy these properties? So this is the first property I want to check. I want to see what does this guy equal to when you multiply it by its adjoint. And the adjoint of the sum of two operators, right? You have the identity operator here, and you have a constant times another operator here. This constant, however, is I. So the adjoint of this thing is going to be the adjoint of each of the operators, but we cannot forget to take the complex conjugate of this thing. And that's part of this process of taking the adjoint. It's the conjugate transpose. So if you absorb this I into the matrix elements of K, right, then when you took its adjoint, you would conjugate every element after multiplying by I. But if we pull the I out, it's the same thing as taking I out in front of a matrix. If you wanted to conjugate this whole object, you would just conjugate both separately, right? So that's what's going on there. So you can't forget to conjugate that I. So this now is the conjugate of this. So let's multiply that out. And if I did this correctly, the first term is just the identity operator's adjoint times itself. So that's pretty clear. That just equals I, right? The identity is a Hermitian operator, and it times itself is I. Then you end up with this term, and that's nothing you can simplify there. But if you look at this term and this term, oh, there's an I here. There's an I adjoint here. I guess I should put that in just to make it clear, right? I guess there's an I adjoint there. But I adjoint is just I, so we can get rid of that I just wrote down. And we can definitely get rid of this I here because that is just doesn't affect things. But these two things do not cancel because K is not equal to its adjoint. But if K were equal to its adjoint, those two terms would cancel. And remember, our interest is this thing equal to I, right? That's what we're curious about. Is it equal to the identity operator? Is it unitary, right? Is T unitary? So clearly, if these two terms don't cancel, this thing isn't unitary. They will cancel if K is Hermitian, right? So now we say, oh, we're onto something here. we've now kind of figured out that this might work if K is Hermitian. If K is Hermitian, then this gets canceled. So let's now add to our candidate for T the condition that K is Hermitian. So that's now a new condition. That's the only way this is going to work as a candidate is if K is Hermitian, right? Now we look over here. Well, we've decided that K is Hermitian. So this actually becomes, right, that becomes, I guess I'm doing this in red, my corrections, right? That becomes K squared, right? Remember, K squared is just, you just apply, if you have an operator K acting on some ket, you just apply that, and then you apply that, and that's the same thing as applying K squared to the ket. That's the meaning of K squared here. And obviously, if it was matrices, you could multiply the matrices together. But we don't generally use matrices here. Anyway, this ain't going away, right? There's nothing to cancel with that. So how do we get rid of that? Well, we think very carefully and we say, well, we do have this delta x squared. So if delta x was actually small, as in dx, then this term would go away because we always drop terms that are second order, right? This would be second order in delta x, which is, as long as delta x is small, we're good to go. So then this does go away, and we are in fact left with I. And so we do have this unitarity step. But now we have two additional statements. We have K is Hermitian and delta x is small. So under those two circumstances, this all works. And what does small mean? Small means you can ignore this term here. Right? This term goes away. So it's actually infinitesimal is what it means. So this operator is a candidate so far. It's unitary when this is actually replaced by, let me get rid of that, dx. That's good, because we know how to take an infinitesimal translation and make it finite. So finding an infinitesimal translation is not a problem, right? So I should erase that question mark, and I can put a dx there. All right, so let's check the next property. So we write down this guy here, which we expect to be additive in delta x double prime and delta x prime. So I'm writing down the translation operator delta x double prime and the translation operator delta x prime. Now I'm assuming K is Hermitian, and I've replaced these delta x's actually with dx's, right? So they're now different, but still both infinitesimal displacements. And then when you multiply this out, you're going to see exactly what happens. You're going to end up with I minus I k hat dx double prime plus dx prime, which of course equals dx double prime plus dx prime, right? So you're going to quickly see that this is satisfied. So that's pretty good. Now the other things that are satisfied is that the displacement, I guess now we got to go with differentials, right? Dx is equal to, the inverse of a displacement dx is equal to t of minus dx, right? That's a property we want to happen in this situation, so that's important too. So this now is our candidate for the infinitesimal displacement. And then we're now going back to the standard Lie group treatment, or Lie operations, or I guess it is a Lie group treatment, but we're not going to refer to that here in this lecture. We know that if I take an operator I minus I k operator, and then instead of putting a differential there, say I go back to my finite move, but I divide by some large number n, but I execute this operator n times on some ket x, right? So I'm taking n instances of translation, which should all sum, right? That's what this is all about. But each individual translation this is a very small number, right? If n is large enough and delta x is small enough, this will be a very, very tiny number, and it'll satisfy this rule of this increment here being very small for any individual step. But you do this n times, and you've actually moved delta x. And then, of course, this whole issue is you take the limit as n is arbitrarily large, right? And of course, this is what the definition of exponentiation is, right? So we write this as just exponential of minus I operator k, right? This is an operator inside here. Operator k delta x, just like that. And that operates on the ket x. And that operator there will work for finite translations, and that is the operator we actually call t delta x. All right, so here we had a nominee, right? We had a nominee, but this nominee was only valid for infinitesimal x, right? So that we really should give that another name, right? Like t infinitesimal, right? But with t infinitesimal, we were able to build t finite, which we'll just leave without anything, and that t finite equals this exponentiation. And what's important about this is all well known, so people who did this the first time, they understood exactly what was going on here. And they now know that k, when you do this kind of process, k is called the generator, right? This is called the generator. And in this case, it's the generator of translations. The generator of translation. So this process has given us, that's why we've by putting it into a narrower and narrower bucket and understanding where you plan to end up, because these steps were obvious to the people. Well, weren't obvious probably, but they wrestled with them. But they know about this process, and they know that k now must be the generator of translations. And what do they know about that? Is if k is the generator of translations, they know that k must be associated with momentum. And they know that because that's what they learned from classical physics, right? Classical physics also has translation operations, and they have generators, and those generators are momentum. So right away they're thinking that k is related to momentum. Now the problem, of course, is that the units aren't correct, right? Because I, k, hat on delta x, right? This is an operator, right? This is an operator. So this literally means, the literal meaning of this exponentiation is always going to be I plus, let me write it out. It's going to literally mean inserting this series expansion for x, for e to the I kx, right? You literally insert that series expansion there. And then what happens is, but by linearity, you end up with the eigenket of x would be applied to each term in the expansion, right? That's what this would literally mean. So we know that we're going to call k hat something related to, it's a momentum operator of sorts, right? And the reason I say of sorts is it is the generators of translations, right? And the generator of translations is understood to be momentum. The problem that we're having is there is a little bit of a unit issue, right? Because momentum, so let's see, what do we have for units? Momentum would be mass times distance divided by time, and of course delta x is just distance. So whatever complex number pops out with the operator k, that must be, so whatever value, I'll call that value k, that value k must be distance to the -1 power, right? The -1. So we have to somehow create a distance to the -1 power with a momentum. And the way you have to do that is you have to divide momentum by something that has units of momentum by something that has units of momentum times distance, right? And what has units of momentum times distance? Well, that's an action, right? And so what you discover is that in order to literally interpret this as momentum, we have to have some constant that has the units of action to divide by k. And then we would be able to write, if we found such a thing, which we would call, say, I don't know, call me crazy, let's just call it H bar, right? H bar is good. So we would then write that that the translation operator for a finite distant x equals x minus I, and then we have the momentum operator instead of k over this h bar times delta x, right? So this is the generator of translations. It's momentum, but you need to have this universal constant of action. And that's not a big deal. I mean, we've seen this kind of thing before. In special relativity, they discovered, there seems to be this universal constant that has units of velocity, right? Units of distance over time. It seems to show up everywhere. Apparently, there must be some constant in nature that is distance over time. Sure enough, speed of light. And in quantum mechanics, the same phenomenon happens, but now we get what we call Planck's constant. And this is how Planck's constant was discovered, by the way. This is just sort of a logical weaving through this process. The point I'm trying to make is the translation operator is now given as this exponential of another new Hermitian operator that we kind of discovered for this process. And that new Hermitian operator we've now identified as the momentum operator. But the momentum operator is Hermitian, right? That's a really important fact. What do we now get to do? Well, let's see. Well, we started with our very abstract and fundamental postulate-driven presumption about the existence of the observable X and its Hermitian operator and its basis states. We posited a translation operator that would act on these basis states in the following way, and we calculated that this operator would have to be this exponential of yet another Hermitian operator. So this new Hermitian operator pops into existence in order to allow us to translate states. And so now we take that new Hermitian operator and we say, well, it is Hermitian, ergo it must be an observable that has its own set of eigenstates. And since it has to do with the translation, it's also going to have a continuous spectra. So now we have this new way of writing any ket, right? Any ket that we might be interested in, right? Any ket, say, alpha, can now be written with a complete set of these guys, right? Where this, I got to do dp. And this, of course, is now the wave function in the momentum representation. Right, so now these wave functions still show up, right? And in principle, we could just write it that way. We could literally put the momentum wave function right in there, right? Actually, I guess I need to write phi alpha of p, right? Because this wave function, you need to know what state you're talking about. And actually, in QED, it's more apt to write it like this, alpha of p. But we'll defer that to later. My point being that there it is, right? There's your state alpha. It's broken down into basis states. The basis states are driven by an observable operator. That observable operator, we're calling the momentum operator in this case. We've actually figured out how the translation operator works, so that's how we define the momentum operator. But now we have a continuous spectrum. Once you have a continuous spectrum, you have the possibility of creating something that in wave mechanics would be called a wave function. And there it is. But we will persist with the Dirac notation, because this is about the Dirac formalism. So as soon as we see this guy, we think function, right? Wave function, right? So now, let's explore this. We now have two continuous, two observables with continuous spectra. Let's explore that a little bit and get ready to start studying the double slit experiment. So to get to the applications, we're going to want to answer a relatively obvious question, which is, given a momentum eigenstate, which is defined like this, right? Just like any observable eigenstate would be. Given a momentum eigenstate, what does it look like if I cast it in the position basis, right? So there's my universal and well-beloved identity operator, right? That's the you can't overstate its importance operator. Maybe that's what we should call it. We'll call it the Yukosi operator, right? You can't overstate its importance. The Yukosi operator, right? Fair enough. Good enough. I finally made a contribution to the world of quantum mechanics. So, but the basis states, we just cast it in the basis state just like any other operator, right? Or just like any other ket. So, and the integration is over dx, right? So this is totally legit, right? And therefore, this guy right here, that is the momentum wave function in the position representation. And we want to know what that is, right? We want to know how to cast momentum operators in position states. That way we can apply, for example, we can now translate momentum. If we know this, we can translate momentum by putting the translation operator right here, right? And we would end up with, x plus delta x xp, right? And that would be the translation of momentum, which is kind of interesting. So we want to be able to do those kinds of things, but we can't do those things until we know, we have to know some facts. For example, we have to know what this is. So let's attack that question. Now, normally to get to this question, we would possibly, well, not normally, but we could use the Schrodinger equation, but we're not going to. We're going to use Sakurai's method, which he's very proud of because he doesn't use the Schrodinger's equation. And it's actually a lot easier now that we've built up the machinery of the translation operator. So consider an arbitrary ket, right? And we express the arbitrary ket in the position basis using the Yukosi operator. And then we translate this arbitrary ket. And the translation just moves right into the integral, right? So it's on the left side and the right side. And we operate on this position ket exactly the way we expect, right? It shifts it by an amount delta x. And that's all pretty obvious, right? This is why we want to cast this arbitrary ket in the position basis, so we can use the translation operator, because we only know how the translation operator works in the position basis. So here we have this thing, and then we're going to make a change of variables. This is where it becomes really clever. This is like, oh man, I wish I thought of that. This is one of the things you probably could have thought of, but just sort of escaped you. Well, I should say me, right? So we change variables to x prime, which equals x plus delta x. And we realize this integral is over all the real line. And when you make this change of variables, you end up basically shifting this delta x from this ket to this ket, right? And now you're integrating over dx prime. So you've now created this inner product. This is still just a complex number. You got to understand, this is just a complex number, right? You've got a ket or a bra and a ket, and that's a complex number. So it's just a different complex number than this one was, although it's sort of irrelevantly different because you're integrating over all of space, right? So it's just a change of variable, right? So very easy step. But this easy step is really important because when we understand, remember, this guy's a function. I keep saying that, right? This guy's a function. It's a wave function. That guy is a wave function. And because it's a wave function, we can use the methods of regular, calculus. And so what is the value of a function when you shift it a certain amount? Well, it's the value of the function at the original position, which is x prime, minus, because we're shifting in the negative direction, I guess, minus the amount of the shift times the derivative, the first derivative of that function. This ends up being an approximation, two p's, an approximation to the value. This guy, this collection here is an approximation to this, to a first order approximation, I guess is the way I should say it. This is a first order approximation. So it's a first order approximation. Makes perfect sense. But you see this partial derivative with respect to x comes in there, and it's operating on this inner product, which is really, remember, this is the wave function, right? I like to point that out because I like to remind everybody that, you know, we can, without much trouble at all, make contact with wave mechanics, right? So this step is the reason we change variables is so we have access to this first order approximation of a function, right? Because as long as x plus delta x lives in a ket, we don't have enough mathematical machinery to deal with that. But once we push it over to this, to this bra, now it's living in an inner product by associativity of all this. And now we can use this first order approximation, which is really excellent. But remember, this first order approximation depends on delta x being small. And so, because it's small on the left-hand side now, we can go with the linear term of the left-hand side. Now, I haven't put dx in here, right? Probably should, right? I should probably swap that out with just dx. But not all that important for now, right? Because it's going to drop out in a minute. So with this on the left side and this on the right side, we can now examine everything term by term. I'm losing my dx prime. It's sort of going off the edge here, but remember it's there. In fact, why don't I put it up here just so you can see that it's there. So the first thing we notice is that this ket, the state ket for gamma, is going to hit this identity operator, and then it's going to hit this term with the momentum operator. Now the term with the momentum operator, it's three constants, I, h bar, and delta x. Those are numbers. So it's really going to be hit by this momentum operator, right? That's the only thing that can really affect the ket. All of this stuff is just scaling by a complex number. It doesn't change the state. This guy is going to change the state because it's an operator, right? That's the whole point of operators. So, but the first part is just the identity acting on the ket, which is just the ket itself. But if we look at this, wait a minute, I'm missing something here. No, I'm not. If we look at this piece in brackets that came from the first order approximation to this inner product, I should actually start saying wave function and point to an inner product just because I want that linkage between inner products and wave functions to be really, really sort of drilled into the audience here. But this first order approximation to this wave function, notice this first piece of it. That first piece of it is literally just gamma, right? So this I times acting on gamma is just this first part. So if we got rid of it, that first part, all we would have left is this second part. And then, so that second part must equal this ket times this stuff here, which is this inner product, its first derivative, times delta x. And so when you look at that way, this delta x will cancel with this delta x. This minus sign will cancel with this minus sign, right? The I will go to the denominator and then come to the top. Oops, I think that might introduce another minus sign. H bar will come to the top, right? H bar will come to the top. I went to the bottom. And then you end up with this expression here. And I love this thing, right? This thing's awesome because what is it? If you look at it, what do we see? We see, well, there's a wave function there, the position wave function for gamma. So we would, think maybe wave function of the state gamma in the position or in the position representation, right? That's what that thing is. And then this is just a linear differential operator that acts on that inner product, right? So it acts on that wave function. The point being is that this whole thing here, when it's all said and done, that's just another function, right? That's just another function. So this guy now ends up playing the role of a wave function in the position representation, right? Because it's still, nothing changes about the independent variable. It's still x prime in this case. Actually, this derivative here should be, this derivative here should be with respect to x prime, right? Sorry, x prime, x prime. So now we know that whatever this momentum operator does on the state ket, on the state ket, it is represented by this wave function, right? Because remember, this is just a ket. I could actually rename this ket alpha. Well, remember, there was a one-to-one correspondence between kets and wave functions, as we talked about. And that was whatever was the coefficient or the component of the basis vector. And that's now this thing. And this operator, this differential operator, suddenly appears, right? Suddenly appears. And notice this doesn't any longer depend on delta x being small, right? If this still will, that was just a way to isolate the momentum operator by isolating the first term of the whole expansion. This is still true in general. So now you can see from wave mechanics this identification of the operator for momentum is identified with this differential operator. See, we've already connected kets with, kets, in this case alpha, with wave functions, right? Here's an example. This is the wave function for this ket. But, in general, it comes back up to here. This is the wave function for this ket. So we've linked the notation or the formalism of bras and kets with the wave function formalism. But now we're linking differential operators in the wave function formalism with these abstract operators in the ket formalism. It's not as easy to come up with these things, but here you go. This is the prescription on how we did it. So that's really important. So the thing that we need to remember for the next step of our analysis, though, is, I'll put a box around it, hold on. So we're going to need this, because remember, our goal is still to figure out what is the wave function, this wave function. We're still interested in figuring out what is that wave function. What is given what we know, can we come up with an actual function, right? The wave function of P in the X representation, right? So we got to remember this step for that. Okay, so the next step we kind of go back to the beginning, right? We say, all right, arbitrary ket, insert the Jacobi operator, right? The Jacobi operator, and now we have the ket cast in the position basis, right? So we say, well, if this is an arbitrary ket, it can certainly be the momentum ket. Why not, right? The momentum ket is a ket. So we now replace the gamma with this, and now we see, or at least we see our guy, right? Of course, that's not very insightful. We literally said that's what we were looking for, so we've not made any jumps, right? So this is what we're working with. So if we were to operate with the bra x prime on the left, right? If we were to do that, we would, obviously we would end up with this expression here, which I just sort of wrote and read up there. But this guy's the delta function. Don't forget, this guy is delta x prime minus x. And under the integral, the whole point of a delta function under the integral is that it basically eliminates the integration and replaces all the x's with x primes, or the other way around. So, since we're integrating over x, we replace the x's with x prime. So it's not the other way around. It's this way around. And so we end up with this integral equals this, which is not very ingenious, right? That was how this was designed, right? It was designed so that the delta function would do this. So we just get x prime p equals x prime p. So that's not interesting, but it's a reminder of how the delta function is applied. So now let's do it in a way that is interesting. Instead of doing x prime p, let's first operate with the momentum operator p on the p eigenstate, and then take the inner product with x prime. So this guy here is, we know how that works. We know we don't know how p would operate to the left on x prime, but we certainly know how it operates to the right on p. And the way it does is it pulls out the momentum eigenstate. This is now a complex number. This is where the hat notation is really critical for me, because I don't have boldface or anything, right? So this is just a number now, the momentum of this momentum eigenstate. And now I have x prime p, which is actually the wave function we're looking for. It's just in terms of the variable x prime, right? We're looking for, the wave function of the momentum operator in terms of x prime, right? It's a symbolic difference only, right? Not much of a thing. So, but with that, if we look on the right-hand side, right, the right-hand side of what we would do, so what I'm doing is I'm operating by p and taking the inner product with x prime. So the point is that if we go back here and we look at p operating on gamma, we get this expression. Now, if we place gamma with p, right, there's no reason why we can't replace gamma with p. And all that does is on the right-hand side is it replaces gamma with p. So we can literally insert this expression with gamma replaced by p into where do I want to put them? Well, I'm going to operate. Well, let's see. So let me make this really clear. Let me get rid of these x's here. The idea is, I'll do this in blue. I'm going to operate by the p operator here, which has the effect of putting the p operator right here, right? So I'm now looking for, this is a ket, this total thing will be a ket, and I'm projecting the ket using the Jacobi operator. Well, the Jacobi operator is right here, right? And this is the ket. So these two kets here match. This ket is congruent with that ket, right? And this is the Jacobi operator. So this is the construction that I'm looking for. So that is I will replace that over here on this side. And if I go into this, that construction with this substitution lands right here like this, right? In other words, this structure here, right, represents p hat on p, right? It's a little even. I mean, this isn't easy, but it is just a matter of substitution, right? So now our differential operator is popped into the story, but we still get, when we multiply when we take the inner product with the bra x prime, we still get this x prime here, which still forms a delta function right there, which eliminates the integral x in favor of, eliminates the variable x in favor of x prime. And so we end up with x prime p, and we divide, remember this is a complex number, so we divide both sides, and we get x prime p equals minus I h bar p over, well, that's obviously a mistake, right? I'm missing my derivative, right? So put the derivative in there, d by dx prime. And there you have it, right? This is a differential equation for the very function we're after. Remember, this is a function, this is a function, this is a differential equation first order differential equation for the function. And the solution for that differential equation is the exponential function, right? This is like the most trivial differential equation you could have. Notice that the sign is now positive up here. I guess to be completely tight about this, I should include an arbitrary real number n, right? And that's h bar. And remember, these are all numbers up here now. There's a tendency to say, oh, wait a minute, the operator p is back, right? But remember, the exponential form of the operator, well, the translation operator, which is an exponential of its generator p, that's a different object, right? This is an operator that acts on kets, because that operator, it's an operator, a function. It's a function of an operator, right? You take p and you sort of stick it in this infinite function. You get this exponential, which represents that infinite series. You can operate on a ket. But this is just a straight up function of a real variable. In this case, the real variable is x prime. So this is the wave function of a particle with momentum p, some specific momentum p, and its independent variable is x prime. It's x prime. And so that is this wave function, right? And so understanding this guy tells us something about the wave function and the probability distribution of finding particles with momentum p, right? But more importantly, it tells us how to cast the momentum eigenstate in the position basis, right? There's the kets that we want to integrate over. But now, instead of writing x p like this, right, I can replace that if I want to have my, I guess this is sort of a mixed notation, right? This is a e to the I p x over h bar, right? And that is the wave function for a pure momentum state, a momentum state of exactly p. And there we have it. And we didn't use the Schrodinger equation or anything similar. And by the way, if you try to reverse this whole process, yes, you could come up with x as some combination as an integral over the momentum kets, and then you will have e to the minus I p x over h bar. If you do this process, you'll see that it comes out the other way. And ultimately, all the mathematics of Fourier transforms start to pop in here. Although I forgot my n, right? I've forgotten my n in these two cases. So what is n? Well, n is always going to be chosen such that we get a delta function normalization, right? So we want p on p to equal delta, or p prime on p to equal delta p prime minus p. And to get that delta function normalization, that implies that n has to be 1 over the square root of 2 pi h bar, right? So I guess I should say that p equals the integral over all real numbers of the x eigenkets times e to the IPX over h bar, right? And then this is dx, and then this p, then there's 1 over square root 2 pi h bar. And I could also then, while I'm at it, just go up here and erase that n and just throw in 1 over square root 2 pi h bar. And that normalization will guarantee that this constant is chosen to guarantee this normalization. That's the normalization constant. So that is what we need to be prepared to do our double slit analysis. So the next lesson, we'll go ahead and we'll kind of exercise this in the context of a very famous problem of physics. We'll demonstrate double slit. We'll demonstrate the idea of interference, all of which are important in QED. I mean, all of quantum mechanics is important for QED. Like, I didn't talk about the Dirac formalism in the context of commuting observables or anything like that. I'm assuming that you know that from quantum mechanics. I'm just kind of going through the formalism. But what's good about this formalism is we were able to derive a wave function without solving the Schrodinger equation, right? We were able to derive it from this analysis of an operator, right? This translation operator. And that's very QED-ish. Now, the next thing we might do when we talk about the pictures of quantum mechanics is we'll talk about the time evolution operator, which is also going to be a unitary operator that when it acts on some ket, we start throwing in this time parameter saying, yeah, that ket is the ket gamma at the time t0. And I want to know, what is the ket gamma at the time t? Well, that's the time evolution operator moves this ket through time, and it changes, just like the translation operator will change a ket. Now, it doesn't change a position ket in the most interesting way, but it, if you move the position of other kets, it might change them in a more interesting way. The point is, this one does have a very interesting effect, and ultimately, this process leads us to a way of deriving the Schrodinger equation, where I should put derive in quotes because it's arguable that that's even a derivation. There's always some assumption in there where people are just uncomfortable enough that they always throw the Schrodinger equation as a literal postulate. Okay, but so what have we done? We started with our curiosity about a continuous spectrum. We introduced the idea of a translation operator on a particular continuous spectrum of a continuous spectrum of the position operator. We derived the properties of we stated what we believe the properties of such a position translation operator should be. We found a candidate for infinitesimal translations. We brokered that to finite translations, and this is your classic case of finding an operator that is the generator of translations, this is what Lie group theory is. Lie algebra and Lie group theory. It's all about these generators and exponentiation of the generators. If you've taken some of the Lie course, this is really familiar. In fact, it's a trivial version of it. And then doing that, we said, hey, we discovered a new Hermitian operator, which we called momentum because it was the generator of translations. So that's leaning on classical mechanics to make that connection. We introduced this constant h bar just to convert the units, but we do surmise that there's some constant out there that will convert those units. That's a bit of an assumption. That's a bit of a theoretical jump, but it works, and it is the thing that quantum mechanics does. And then, in addition, we discovered the connection between wave mechanic differential operators for observables and our abstract Dirac ket notion of operators that are observables. We found how to make that connection in at least one case, and it's an important case. We now know that in the wave function language, the differential operator for momentum is IH bar times his first derivative, expecting to act on a wave function. We've already made the connection between wave functions and inner products, so that's good. So we've bound the two formalisms together, and doing that really, I think, it deepens our understanding a lot. And I know it's just formalism, but hacking through it really makes us understand sort of where this theory came from. And then ultimately we found, we kind of jumped into the wave function formalism, and we found the literal value of an inner product. We found the wave function for an eigenstate of the momentum operator. We already kind of know the wave function for the eigenstate of position operator, but now we know it for the momentum operator in the position basis, right? That's the whole point, in the position representation. So we have found the wave function of the momentum eigenstate expressed in the position basis, and that's what this is. And with those things in hand, we can now switch between the momentum basis and the position basis. And that is the secret to understanding the double slit experiment. which is what we will do in our next lesson. Okay, thank you very much.